Hi everyone and good morning. Today we will, the objective of our lecture today is to go through the macro structure of the course, or why we are studying numerical method. It's very important before we starting from next week to go into the details of the course, is to try to find or to try to answer the question why this subject is important to me as an electrical or a computer engineer. So that's what we'll be answering today. I will be allowing some time for questions, concerns about the course at the end of today's lecture. And also, if I may ask you, please try to switch off your camera so that the bandwidth will be okay. So the question is why we need to use numerical method. What is the point of using numerical method? The answer, or the simplest answer to this question, is to solve problems that we cannot find an exact solution. So we are trying to solve some engineering problems, could be electrical, could be computer, could be any other engineering disciplines that we don't have a closed form solution to it. So take this example you studied in physics, when we try to find the electric field around a conductor. So in this, we use Gauss law, if you recall from physics. Gauss laws that the total flux that is leaving this closed surface is equal to the charge enclosed with this volume. And the way we do that numerically, we will take double integral of the field equal to the enclosed charge divided by epsilon, which is the dielectric constant. Okay. Now, from this, if you solve it, of course, this is not our concern, but this is how we find the electric field equal to the charge divided by a constant and the distance x. This can be done only if, someone said, I cannot hear you. Is there no sound? Okay, so it seems that, okay, so someone was complaining about the sound, so there might be a problem in their system, audio system. Okay. Okay, let's go back. Now, if I have a much more complicated system, like for example this is an overhead line, and in these overhead lines we have these insulators that carry the conductor. These are the conductors that we use to transmit power. Okay, and at the connection point between the insulator and the conductor, we have what we call corona ring, something to minimize the electric field. So it's a very complicated system. Now we need to calculate the electric field along the surface of the insulator, because if the electric field was high enough, it might cause damage to the insulator. So we need to know how much is the electric field. No way I can apply Coulomb's law, Gauss law, or any other law that we know about the electric field. So the only way to solve this problem is to use numerical method. And we use something called finite element, finite difference, and some other numerical methods. So when you look here, this is the electric field along the distance. So this is starting from this point, going upwards from zero. This is the zero, the connection point, and as you go up, and this is the electric field, or the electric field in the without and with this corona ring. Of course, that's not our subject, but this is to tell you why we need to use numerical method. Whenever we have a problem that we cannot find a closed form solution, then we have to use numerical methods. Or it is difficult to solve using hand calculations, then we go for numerical methods. In this course, we will apply numerical methods in different applications: linear, nonlinear equations, curve fitting, differentiation, integration, ODE, ordinary differential equations, and optimization. And I will try to go through these topics one by one and show you some examples of electrical computer engineering problems and maybe some other even more generic engineering problems that we need to use numerical method. This is to excite you about the subject. So when you talk about solving linear equations, so this is from your circuit course. If I want to find the mesh currents, I have 5 unknowns, then I have to have 5 loops. So I end up having 5 simultaneous equations that I need to solve. Now, solving a 5 by 5 system by hand is not really impossible, but it is a bit difficult to do. Now, imagine if my circuit is 100 by 100. You have 100 mesh loops. So then that becomes almost impossible to solve it by hand. Then we have to use a numerical method to solve those simultaneous linear equations to find the unknowns. One thing you will be studying, I think some of you might have seen that in high school, which is this symbol. Okay, we call this diode. Okay, the diode allows the current to go in one direction, and the current in the other direction cannot go. So only one directional current. This diode will have a current called ID that go through it, causing a voltage drop. We call it VD. The relation between still I am getting some. Just a second. Let me check here. Same problem, the sound problem. Guys, do you have a problem or? Okay, I think let me just respond to you. To only, yeah, I think the student only. Just give me a second. Let me respond to her because it seems that she has a problem. Okay. Okay, so the relationship between the ID and VD is nonlinear like this one. Okay, and we want to find this voltage, this VD. As you can see here, it's a very nonlinear system of equations. And sometimes we have multiple diodes. So we have more than one equation, and all of them are nonlinear. Now, how to solve this? There is no way you can solve this by hand calculations. Then you have to use numerical method. And we will have this example later on. This is for only electrical engineering students. By the way, guys, my background is in power engineering, so I will be a little bit biased towards power. I will try to push myself back and give more generic examples from your background. You will notice as we move on in the course, I will try always to bring some engineering problems related to your field. I know you did not take much courses, so I will try to use circuit and some general information like sensors. That's something common between you guys. I will try as much as I can to be away from power, because I know only electrical engineering students will take power courses. But this is an interesting example. This is a sample of a power system where we have generators and we have loads that consumes this power. Okay. Now, the system of equations that we solve is a system of nonlinear equations. P is the real power, Q is the reactive power. So what we want to find in solving this equation, we want to find the voltage and their angle. The voltage and their angle. As you can see, this is a highly nonlinear equations, because how to find an angle of a cosine function. So this is also another example where we need to use a set of nonlinear equations. This is a very general example from mechanical engineering. Okay, so we have a trunnion that I want to fit it here, but usually the size of this one is bigger than this, so it cannot be fit. So what we need to do, first we cool it down to certain temperature so that the diameter will be able to enter, and then we leave it to warm up so that it will not go out again. The equation for this that we need to solve is this. As you can see here, this is a highly nonlinear equation that you cannot solve using normal ways of like things that we know about solving linear equations. So this is another nonlinear equation that we have to solve. And there are tons of examples of nonlinear equations that you will see in your engineering discipline. Another application, a very interesting application, is a curve fitting. What is a curve fitting? You are getting certain points. You collect those points from some experimental work, from data from the field, and you want to fit a curve, like that curve represent these points. To do the curve fitting, there are two different ways we will learn about. The first one, we call it regression. In the regression, we will try to find a curve that goes through the points, not necessarily passing through all the points, so that it will minimize the error. So for example, if we have these points, what is the best line that can fit these points so that the error, which is the difference between the point and the curve, this is called the error. So we'll try to minimize this error. We use something called the least square technique. The curve, this is linear, could be nonlinear. So in regression models, we will try to minimize the error by finding a curve that best go through the points so that the error between these points and the curve is minimized. What is the use of this? Why we need to do something like this? This is a very interesting example. As you know, renewable energy become part of our life. And before that, we have what we call thermal power plants. That is, thermal power plants like nuclear reactors or the generators that are based on burning something, burning oil, burning natural gas, etc. Those systems, we know exactly how much power we get from them. So if I'm burning an X amount of oil or gas or nuclear substance, I know I will get Y amount of power. So the amount of power I'm getting from my generator is deterministic. I know exactly how much it is. And this is very important to plan my power system. Now, when it comes to PV or wind energy, it's very stochastic. I don't know actually how much power I'm getting after 5 minutes, after 10 minutes. Why? Because the speed of wind is keep on changing. The amount of solar energy I'm getting because of clouds, because of pollution, different factors is not constant. I don't have control over it. So what is the solution? The solution is to build a model that I can use it for a forecast. So one of the application of regression is to build a system or to build an equation that can be used to predict what will be the output power after 10 minutes in the future. This is the simplest machine learning algorithm you can have. If you study machine learning, the first thing they will talk about is regression models. Okay, so for example, here I have these scattered points are actual points coming from measurement. Okay, so then this are the actual ones, then I'm using a fourth order polynomial, a fifth order polynomial, here's sixth, seventh order polynomial to best fit these points, so that if I want to schedule or to know the power after 10, 20 minutes from now on, I have a function that can be used to predict this. So this is one of the also it helped me also to predict, as you can see here in the curves, not just on time, but the relation between the wind and the power itself. So if I have this amount of wind, how much power I'm getting. So it is both as a time, and usually what we do, this has a step before that. Usually we have, this is time and this is wind speed. The wind speed, we get it from, for example, Canada environment. So they have certain data in the past. So we have it here, this data from the past. And from this data, from this wind speed data, I come here and try to predict the output power. So that's opened a huge area of research, because without the ability to be able to predict the amount of power from wind, this is a huge limiting factor. And now with those sophisticated mathematical models, we can predict the output power of wind, so we can integrate it in the power system. Another way of curve fitting is interpolation. So interpolation is also a curve fitting technique, but the difference between regression and interpolation, in regression, we will try to find what is the best curve that go through the points or part of them to minimize the error. However, if you look to interpolation, we will find a function that goes through all the points. Okay, so if these are the same points, in interpolation, we'll try to find a curve that goes through all the points. In regression, we will find a curve that goes through some of the points, but try to minimize the error. Now, why? What's the difference between the two? Why we need to go sometimes for regression, and why we need to use interpolation? For regression, there is always noise. There is always measurement mistakes when you take, especially when you take measurement in the field. So this is why if you try to overfit, you try to find something like this, it's called overfitting. You can find 10th, 15th order polynomial that go through all the points. Okay, but when you try to predict something new, it will be awfully wrong. Okay, so this is why we need to have the regression. Now, and sometimes, for example, here in a thermistor, what is a thermistor? A thermistor is a sensor that we use it to measure temperature. Basically, it has a relation between the resistance and the temperature, as you can see here. Now, every manufacturer will do a very controlled experiment, so that will give you this curve. And you can see here clearly that I can fit a curve here easily without the need to use regression. Sorry, it can be going through this. Okay, so this curve can help me when I want to find the temperature. For example, if I have something here at 700 ohms, so what is the temperature? So I use this curve that I predict, or I can extract from the data, so that I will know what is the temperature. So basically, the thermistor is a device, a nonlinear device that can be used to measure the temperature by measuring its resistance. So measure the resistance, and then from that we convert it back to temperature. Now we will have again detailed examples later on about how to implement the curve fitting here in the thermistor. Derivative, of course, we know derivative very well since in high school we studied derivative, and we know how to find the derivative. In the derivative, it's defined as between 2 points, f of x plus delta x minus f of x divided by delta x. So this is the definition of the derivative. Now, for example, if we have an f of x equal to x squared, all of us, we know that f prime of x is equal to 2x, okay? So this is if we want to do a derivative for a function that can be easily, we can easily find the derivative of. However, sometimes we have a curve. We don't have a function. Now we can do that in 2 steps. First, estimate the function using regression or interpolation, and we will have examples like this. And then, once you know the function, take the derivative. Or I can directly find the derivative by applying the same definition here. But now delta x cannot go to 0 because, remember, this is a numerical method, and if you divide by 0, you get infinity. So delta x will have a finite number, not 0. So for an instance here, this is your delta x, and you can see here, if you want to find the derivative at this point, or at this point, this will be a huge error because your delta x is large. Now, if you reduce delta x, you will have a better estimation of the derivative. And as you keep on decreasing delta x, you will get a better and a better estimation. And this will lead us to something very important that we will start our discussion next week, which is the error. In numerical method, there is always an error because I cannot have a delta x equal to 0. I can have delta x a small number, but that's not equal to 0. And hence, there will be certain error between the actual value and the numerical value. And we need, one of the things we need to work with is how I can minimize this error. And what is an acceptable criteria or acceptable accuracy? And what is the criteria for that to reach this accuracy? This is what we'll be discussing next week. Now, derivatives, as we know, this relation, we have seen this in circuit, that the current across a capacitor is equal to C dV by dt. So if I give you the voltage waveform, I can find the derivative multiplied by the capacitance, and then I can find the current, which is something like this. So this is the current from this relationship. Now, if I have these curves and I want to find the current, I don't need to do the derivative like this. I can just apply numerical methods and I can find the current in the capacitors. As in engineering, we know the relation between the acceleration, voltage, and displacement. So if you take the derivative of the displacement, you will find the velocity, not the voltage, the velocity. And if I take the derivative for the velocity, I will find the acceleration. So this is something from basic physics. Integration is the opposite. So in the integration, we'll try, if we take the derivative of a function, as you know, if I integrate that function, I will go back to the original function. And this is the notion. This is how we do the integration for certain functions. Now, sometimes it is almost, as we will see later on and give you functions, it is almost impossible to do the integration for these functions. So we need to come up with a numerical method to find the integration for very difficult functions, or if the data I have is coming in the form of points, data points only. Again, as I said before, for the derivative, the same apply for the integration. If this is the case, I can find the integration in 2 steps. Estimate the function and then take the integration. But even if I estimate the function, the integration could be very difficult to be done. So I can do that directly. And the way we do that, actually, integration is basically an area under the curve. So basically what we can do, we can divide this area into different smaller areas and then find the area of those smaller areas. Now we can, how we will estimate this, we could estimate them as rectangulars or trapezoidal or higher order functions. We will see all of this and we will see what is the impact of the different ways of doing the integration. Again, integration, we have seen that in circuit. if you have the power and if you want to find the energy is basically nothing but the integration of the power. So if the power is giving with this curve with certain integrations, we get this. Again, if I want to do this, especially if I have the power and I want to find the energy consumed, and these power are just points, not a function, then it is much more convenient to use numerical method of integration to find the energy. Now, back to this, same thing, that going from displacement to velocity and velocity to integration, I can go down by taking the integration. So if I integrate the acceleration, I will find the velocity. If I integrate the velocity, I will find the displacement. First order systems. Again, in circuit, you worked with first order systems. So for example, if we have an inductor or a capacitor, and I come here and open the switch, and I want to represent this system by a first order differential equation. So, and I think you used the step-by-step method to solve this, but later on you realize that we can solve the differential equation directly. So we will have applying KVL. So the voltage across the inductor is L di by dt. The voltage across the resistance is Ri equal to 0. So this is a first order differential equation, homogeneous, linear. Then there are different techniques to solve them. Now I can solve these equations in a numerical way, and we will see this. Now, if I add both the capacitor and an inductor, this is, you may not have seen this. I think it's in another circuit course. But you will see those second order differential equations. Now again, applying KVL, the voltage across the resistance is R times I, and the voltage across the inductor is L di by dt, and the voltage across the capacitor is V. Now this equation has two unknowns. It has the current and it has the voltage. So I cannot actually solve this equation because we have two unknowns. So we have another equation, which is I equal to C dV by dt. So the current that goes through the capacitor is C dV by dt. Or I can substitute I with its value here. So it will be R C dV by dt. So I just substituted I of t with its value plus L di by dt. So I will take the second derivative. So it becomes LC second derivative dt squared plus V equal to 0. So what do we have here? We have a second order differential equation. Okay, so usually the best way to do that in a closed form is to use Laplace. Laplace is the best to do that. However, sometimes we have much more complicated system, many second and first order differential equations. Then we have to use numerical method. And this is very common, not just in electrical engineering, but in all other engineering disciplines. Just take an example here. This is from mechanical engineering. If I have a mass, and this mass I pull it by certain force, the force is equal to mdv by dt. Okay, so we have only one system that can store energy, which is, or we call it one energy system, which is the mass. The mass is the only energy system, so we can represent the system by a first order differential equation. Same thing here for the circuit. When we have one energy storage element, we represent that by first order differential equation. When we have two energy storage elements, then we have to go for a second order differential equation, and other engineering systems are no exception to this. So here, for example, it's more complicated. If we have a friction here, still it is one equation, one unknown, which is the velocity. Okay, now if I add a spring to the problem, then the spring is another energy element that can be storing energy, and the equation will be modified as such. Now I have the x as the distance as unknown and the velocity as an unknown. Again, one equation, two unknowns, I cannot solve them. Then I have to find another differential equation. And in this case, as we know, the velocity, we talked about that, is equal to dx by dt. If I come and substitute here, then I will have a second order differential equation, same like what we have in circuit. And that's not just the case of electrical mechanical. If you study engineering systems, if you go for fluids, thermals, structure, you will always see the same thing. You will always see the need to represent the system as a first or a second order differential equation. And when you deal with a huge system of differential equations, yes, if I have one equations, we learn that in differential course that yes, we can deal with it. We can have different techniques to solve them. But if I have a system of differential equation, then it's impossible to solve them using hand calculations. And as a matter of fact, the system I showed you at the beginning of today's lecture, which is how to find the electric field of an insulator, it's basically a system of not differential equation, but partial differential equations. And to solve these partial differential equations, you have to use numerical methods. In this course, we will not deal with partial differential equations. We will deal only with differential equations. Now, there are other specialized courses just how to deal with differential and partial differential equations. You will find a course only in finite difference method, which is a method that we will touch a little bit. Can be used to solve those complicated systems. A finite element is another course, and you will find this course not only taught by electrical engineers, but taught by mechanical engineers and taught by civil engineers as well. Finally, the last example and the last topic we will be covering is optimization. And again, optimization by itself is a huge area. And you will find courses in optimization in electrical engineering and more into engineering management. We have here a department called engineering management. This is one of the departments that deal a lot with optimization. So what is optimization? What is optimization basically? Basically, you want to minimize or maximize something. Minimize the loss or maximize the benefit. This is what is optimization. However, there are certain constraints that you want to pay attention to. So it's not just minimizing and maximizing, but there are certain constraints that you have to pay attention to. So here we'll cover it in just a week. We will just cover one or two methods, very simple methods, just to introduce the topic to you. But this is a very huge problem. So I'll give you just here an example. Imagine here a power system that we have multiple generators. And these generators, all of them are thermal power plants. So they have a function of the output power and the cost. And they are not identical because you will find that some generators are old, some of them are new, some of them use different technologies. So the cost function is different. Okay, now I want to use all of those generators or some of them to meet the load condition. So how much I should get from each generator so that the total cost of my generation is minimized. Okay, the problem as such would be easy. However, there are certain constraints. For example, there are certain overhead lines. I cannot have more than this amount of current. Why? Because this is what we call the limit. If we try to push current more than the conductor can take, this will lead to big problems. So we do not exceed the thermal limit of the conductor. Also, another limit, I want to make sure that the voltage is within certain tolerance. And why is that? Because, for example, in your house, the voltage is 120 volt. I want to make sure that this voltage is within, let's say, plus minus 5%. I don't want to have the voltage as 200 volt so that if you bought your appliances, it will be damaged. Or I don't want this voltage to be 60 volt, so when you try to run your appliances, they will not work. So this is one of the constraints of the voltage, constraints of the current that I have to meet. So it is a very interesting subject, a very interesting area that work with systems, as you can see here. And the objective here is to find this total amount of power that I will get so that my total cost in the system is minimized, but at the same time, I'm keeping the system working. I'm meeting all the constraints in my system. Also, optimization can be used on a component. This is what we call an underground cable. If you live in Waterloo, you might have seen that there inside the city, there are many poles with overhead lines. Those, we call them distribution lines. And we use them to distribute the power to our houses. You will find that those poles connected to some of them a transformer, and this transformer is used to step down the voltage from that voltage level, which is usually here, it's around 22 kilovolt or 13.8 kilovolt or 11. There are different voltage level, different systems. This voltage level is very high, so we step it down to the 120 volt. We use it in our houses. Now, overhead lines are a cost-effective method, but in some cities, like for example, in highly condensed area, like downtown Toronto, you don't want to have those overhead lines inside the downtown because it's very dangerous. And it will be also very difficult to do because the downtown of the city is very congested. So you need to have an alternative. So we use an underground cable to distribute the power between the generation to the houses. Now, one of the parameters we want to find, this is the conductor that carry the current, and then there is an insulation around it, around this cable. Now, this insulation will have an electric field. One of the things I want to make sure that the electric field stress on the insulation is minimized. And why is that? Because if the electric field is high enough, this might damage the insulation. So I want to minimize this. So again, this is an optimization problem. So the relationship between the electric field and both the radius of the conductor and the overall radius of the cable is given by this relationship. So if I want to find what is the best radius of the conductor so that my electric field is minimized, this is the relationship. So if I draw this relationship, you will find that this has certain minimum point here. So the radius will be something around this point. Now, there are some other constraints we have to impose on this. For example, for this cable, I have to use a minimum radius. Why? Because the current requirement is such. So this radius is not sufficient for me. I need to have a bigger radius. So this is the minimum I have to have. So sometimes even the optimum solution is not good for us because we have constraints that we cannot violate. So that is the optimization problem, and it is one of the very common application of numerical methods. Okay, so I will stop